Hello everybody, welcome back. We are going to start a brand new topic, stereoisomers. What are stereoisomers? Stereoisomers are molecules that have the same molecular formula. They have the exact same connectivity, but they have different spatial orientations. So let's write that down because that's important, and then we will get to chirality. Chirality is a property of some of the stereoisomers. Stereoisomers are molecules that have the same molecular formula. That means all the atoms are the same. And the same connectivity, that means they are not constitutional isomers. If you look at them, they look like they're the same molecule, but the spatial orientation of the atoms are different in the molecules, but have different spatial orientation. The molecule, atoms inside, or groups of atoms inside. So we're going to look at some stereoisomers and some definitions here. So objects that have the same molecular formula and connectivity have different spatial orientation. How can we tell them apart? Well, we have something called a plane of symmetry that would tell us whether something is going to be a stereoisomer or not. So we have like a plane of symmetry test, you could say. Let's take this object, for example. Is this going to have a mirror plane of symmetry? How can we tell? Well, take this and, well, pretend you have a knife and cut it in two. You get exactly 2 equal halves. That's a plane of symmetry. Or let's say you have a mirror and you reflect it in the mirror, and then the mirror image is identical. Literally like put it on top of the mirror image for this molecule, and you will see that it's going to overlap or superimpose. That's the word we use for overlap here. So it has a plane of symmetry. I mean, next time you go into your kitchen or your garden, look for things that have plane of symmetry. You'll see plenty of things have plane of symmetry. In fact, I had a hard time finding things that didn't have a plane of symmetry. But if you take, for example, natural products like this, a lot of your fruits and vegetables, you can cut them in equal halves here. It's got a plane of symmetry. Why is that? Because the genetic code is a lot simpler if you have a plane of symmetry. You don't have to have very fancy DNA coding for that. And besides, it's more functional. Even man-made objects, I'm just bringing my son's toys, he likes these. So if you take these, you can see, you can cut them exactly in two. And so it's got a mirror plane of symmetry here. And if you have, let's say, lots of man-made objects have a mirror plane of symmetry. How about this bird? Hello? Do I have a plane of symmetry? What do you think? Yes, I do. I can see.
Yes, I do. Do I have a plane of symmetry?
Cut this bird in half, and you'll have half a bird here and half a bird there that are exact reflections of each other. Okay? So, yes, I'm beautiful.
Yes, I'm beautiful. Yes, I'm beautiful.
And symmetric.
And symmetric. And symmetric.
Right. So let's write that down. So objects that have a mirror plane of symmetry are called achiral, are not chiral. Molecules that have a plane of symmetry. And we just said what that was. We can cut it in exact halves. Achiral. And for example, you cut it in half, and you can take that half and you take a mirror image of that, and you can superimpose that mirror image onto the object. So if this is your mirror image, the mirror image looks exactly like this. And you can see you can superimpose that. They're identical. So achiral molecules can be superimposed. Molecules can be superimposed. That's kind of like overlaid on their mirror images. Okay? A lot of natural things, in fact, a lot of beautiful things are not chiral. For example, take this shell. You really cannot cut it into equal halves. You cannot, even this way or this way. So this is what we call a chiral object. All right? Lots of natural products are chiral. And here you go. There's some function to it, and there's some beauty to it. And so these are chiral. Sometimes even man-made objects can be chiral. There's no plane of symmetry here, or this is kind of on the side, so you can't really cut it into equal halves. So you have to look at all of the ways in which you can cut, not just in one plane, like across all of them. Let's take this cherry moya, for example. You know it's not equal on both sides. So this is achiral, but we got to test it in every direction first before we come to a conclusion. Because some objects can look like they are achiral, but when you turn them around, they could become chiral. So here, if you take this cherry moya and cut it in two, and try to reflect it in the mirror image is not exactly the same as the other side. So the mirror images are not superimposable, unlike in a chiral object. So let's write that down, because that's a very important definition. So objects that do not have a plane of symmetry are chiral. Molecules that lack a plane of symmetry, so you shouldn't have a plane of symmetry in the entire molecule or the entire object, are chiral. Comes from the word chi, which is the handedness. So you can't really superimpose this on top of this, you see? So they are non-superimposable. Their mirror images are non-superimposable. And how did they come up? How did they even discover that molecules have a plane of symmetry when they can't even see them? Well, it all started off with a very sad story. In the 1950s, there was a company in Germany that made a molecule called thalidomide, and I think most of you may have heard of this by now, given as a sedative. But then this is the time when, women's lab and all of that, and women were going out to work, and morning sickness was a huge issue. So they gave these molecules as a preventative for morning sickness, okay, so they could get to work and do their job just like all the others. Well, it so happened that, and it took them 5 years to figure out what was going on, and it took them 5 years to figure out that this was the molecule that was causing a tremendous number, more than 10,000 birth defects. These are severe birth defects, children born with their hands attached to their shoulders or their feet attached to their thighs. I mean, a tetragen, okay, that's like a deadly one. And it was really sad that it took so long. The good news is in the United States, the FDA actually rejected this drug because they weren't very happy with clinical trials. So, that's something nice about stringent rules here. Of course, it takes a long time for drugs to come out, but for good reasons. So this is a tetragen and caused a lot of birth defects. And then they discovered, well, there is a mirror image of this molecule that's actually a sedative. And this one was the one that was causing all of the harm. So all molecules that lack a plane of symmetry For example, this molecule doesn't have a plane of symmetry because you have over here a center that you cannot cut in half. So it has huge implications for the drug industry. And right now, a lot of the drugs that we take have both the molecule and the mirror image. So 50% of the drug really isn't even working on us. But in this case, 50% of the drug was actually killing people or causing birth defects. So 50% might be a medicine and the other 50% might be a poison. So there is a big push to make only the chiral molecule that's effective. So we have like S-ibuprofen because we don't want to have to take both and then have our kidneys then flush out all the unnecessary parts. So here, that's the main reason why we then got into this huge research because of thalidomide. Okay, so let's look at molecules now and chiral centers in molecules. Here's a molecule here. So let's pretend these are carbon-carbon bonds and maybe carbon-chlorine bond. Is this chiral? Well, look at the molecule. What do you think? Can you cut it in two? Yes, you can. You can cut it in two here, right here, through the middle of this bond, and it's chiral. Or you can cut it like this, here, like this, and you can have two equal halves. What if I have two things that are different on this molecule? Is this chiral or achiral? Well, if you look at this molecule, you can take a knife and cut it through this blue bond and the yellow bond here and have two equal halves. So yes, it's got a plane of symmetry, therefore it's achiral. Let's look at something that's got three different things on it that are different. All right, so over here, is this chiral or achiral? What do you think? Can you cut this molecule anywhere in two and get two identical halves? What do you think? Well, you can try it out. Well, if I cut it like this, it's black and blue. If I cut it like this, it's green and blue. So in every way that you can cut it, you get two halves that are not equal. Well, we can try it out and see if I take this and let's say I take a molecule with the same molecular formula, they're all connected to the same things, and they have the same connectivity, right? This yellow is not connected somewhere, it is all connected to the center just like here, but they have different spatial orientations. Look at this. In this case, blue, green, yellow goes clockwise like this. In this case, blue, green, yellow goes counterclockwise like this. You see, so the spatial orientation is the only thing that's different. And because the spatial orientation is different, you can see that this, if you put a mirror here, will reflect this as the mirror image. Now, the next thing is, are they superimposable? That is, can I align all of these bonds with all of these bonds exactly? So, well, let's try to align them. If I align two of them don't match. Well, let's try aligning the blue and the green. Oops. If I align the blue and the green here, then the yellow and the blacks don't align. So if I align two of them are not going to align. So that means I cannot overlay this molecule exactly on top of this. I cannot, however much I try, in whichever direction I try. These are non-superimposable mirror images. So we have a name for that. Non-superimposable mirror images are called enantiomers. All right, so these are chiral molecules. They have chirality. That means they have a handedness, either a clockwise orientation or a counterclockwise orientation. Okay, and they're non-superimposable. So enantiomers are a kind of stereoisomers, molecules that are non-superimposable mirror images. Okay, now how can I tell them apart? Let's say I want to buy this because this is my medicine and this is my poison. I don't want this. I want to buy only this. So how do I order this? And how do I name it? Because all of the connectivity is the same. Let's say this is chlorine, bromine, iodine. So this will be bromochloroiodoethane. This will also be bromochloroiodoethane. You see? So the only thing that's different is again the chirality or the handedness, the clockwise, counterclockwise. So I got to use that to kind of differentiate between these two and tell whoever, Aldrich or VWR, okay, send me this, guys, don't send me this. So we got to try to distinguish between the two of them using the only property that's different. So how do you know in a lab or in a physical sense that these two are different? Well, they found out that if you shine a light through a achiral molecule, it's just going to fall right where there's no deviation. And plane polarized means these rays are coming only in one direction. So it's going to go exactly where you had it. But when they put a chiral compound in a test tube and put it in front of this plane polarized light, it kind of deviates from its original pathway and goes maybe clockwise, maybe like 10 degrees or 20 or some number over here. And then there's some intelligence here in these photons that it knows which kind of direction or what chirality it is. If you put the other mirror image, it goes in the other direction. And you'll get a light spot on the left hand side. So let's say this was, 50 degrees to the right. This would be 50 degrees to the left, counterclockwise on the screen. So that was a major breakthrough. So we can tell the handedness from this and this by using some rules. So we can order it. All right. So let's say, how do we tell apart a molecule that is R or S? So we have what we call Kahn-Ingold-Prelog rule. So Kahn with a C, Ingold-Prelog rules. First is, these are going to have a molecule would have a stereocenter. So you got to find the carbon or the nitrogen that is the stereocenter. Find stereocenter. And typically stereocenters, not always, but most of the time, stereocenters will have 4 different things connected to them. X, Y, Z, and let's say maybe a hydrogen or a carbon. I will just put A. 2. Then look at each one of those atoms that are attached to it and look at the atomic weight. So prioritize groups attached to that chiral stereocenter according to atomic number. Then we can use that to assign. So put the least or the lowest atomic number away from you. Let's say this is a hydrogen and these are halogens. So you will put it away from you. So this is important that you put away lowest priority, in this case atomic weight, group, atom or group away from you. 4. So then you look at it from the opposite side of that lowest priority. Look from opposite side of lowest priority group. Then if it goes from highest to lowest in clockwise direction, the other group's highest to lowest. So 1, 2, 3 goes counterclockwise, then it's defined as R. Re and C, right turn and left turn. It's like on a freeway, you make a left turn, that's S. If you make a right turn, that's R. Highest to lowest counterclockwise. So that's going to be 1 to 2 to 3 in this direction, counterclockwise. Then it's labeled S. Let's do an example to kind of understand what this means. So let's say you have a carbon and then you have 4 different groups around it. You got to put them in a wedge and dash because as you can see, this is all about spatial orientation. How would you know what the spatial orientation is if you don't put these wedges and dashes and if you just put lines? They're coming out, coming in. It has to be 3D diagram. That's important. And here, let's say you have a mirror image of that. And of course, right now, let's put some groups on it. Let's say you have a carbon here, hydrogen, let's say a fluorine here, a chlorine here, a fluorochlorocarbon. And over here, let's draw the mirror image. Again, what's behind is going to be, this is just a mirror image. Chlorine and CH3. So kind of like this. So this is your carbon, chlorine, hydrogen, fluorine, and same on this side, you have carbon, chlorine, fluorine, the mirror images. So here, that's prior, so find the stereocenter, that's the only stereocenter here. So we can sometimes put a star here, that's your stereocenter. Groups it according to atomic number, all right? So you can get a periodic table. You know hydrogen's only 1, so it's always going to be your lowest priority. And then fluorine, and then chlorine and carbon. So first you have to look at the things that are directly attached to it. Don't count this as a methyl, count this first as a carbon. So this carbon is 12, 19, and 35.5. So you have to 35.45. So you have to go up exactly by the periodic table. So chlorine would be the highest, then the fluorine, then the carbon at point of attachment. Same here, 1, 2, and 3. Then put the lowest priority group away from you. Okay, well, I've written it as a dash. That means it is going away from me. So I don't have to rotate this. And look from the opposite of the lowest priority group. So I'm facing it and I'm looking at it from the opposite of the lowest priority group. Then if it's going clockwise, that's R. Let's see, so here's your chlorine, fluorine, carbon, and whoa, you're making a right turn. This molecule would be labeled R. Then you can name it R, 1-chloro, 1-fluoro, ethane. Over here, then you're going to do 1, 2, 3. You're going to make a left turn on the freeway. All right. That's going to be an S. And the name is going to be the same. 1-chloro, 1-fluoroethane. So the names are going to be the exact same because their connectivity and the molecular formula are all the same. Only thing is the spatial orientation, and that we denote by R and S. And let's look at some molecules. Well, let's see. I have a molecule like this that I'm going to determine if it's R or S. Here it is. Here's a molecule. And let's say you have a chlorine or a bromine here, and then a methyl. Just do a simple one for right now. So the mirror image of this is going to be exactly the same, except here your chlorine and your methyl are going to be facing left. So it's just a spatial difference. Everything else about this molecule is exactly the same. So how would you do something like this, where you have a, let's say, a double bond here and a double bond here? First, find the stereocenter. So these are CH2s. If you have two things, even two things that are the same, we saw that you have a plane of symmetry. So let's say you have two hydrogens here, you can cut right through here and get a plane of symmetry for this molecule between this and this. So if you have two hydrogens, that's achiral. What about these? Well, if you take an alkene, we learned that it's sp2, it's flat. Anything that's flat doesn't have any chirality. You got to have a three-dimensional structure for it to have chirality. Flat things can be cut right in half, so therefore this is achiral. What about here? Oh, well, now that gets a little bit more interesting here, because this carbon here has a chlorine, methyl, a double bond, and a CH2 attached to it. So 4 different things. So obviously we cannot have a plane of symmetry there. You cannot cut this molecule in any way and get 2 equal halves, right? You can see that that's pretty obvious. If I cut it in 2 like this, then I'll have a chlorine and a alkene. If I cut it like this, I have this ring, and then this is different. If I cut it like this, I have a chlorine up and an alkene here. So in every way that I cut this molecule, I'm not going to ever get 2 equal halves. And so it's the same here, because it's just a reflection of that. So now that we found our stereocenter, then we can go around, go to the next one and assign priority. Well, here's a carbon and here's a carbon. Well, which one's better? Which one is more important? In that case, when you have two atoms that are same, then you got to go down the chain and see, which one has got higher groups. Basically, the heavyweights get high priority. So they get top seating, like balcony seating. Then the hydrogens and all just shoved in a corner. They're the lowest priority. So over here, if you take this, you have a chlorine and a carbon and a carbon and a carbon. So in this case, you have a high priority group that is chlorine, and without a doubt, that's going to be number 1. Then you take the carbons, 3 different types of carbons. So then we have to see what they're connected to. Carbons with 3 hydrogens. Hydrogens are nothing. They're just like, 1 s orbital and 3 protons there. So that's really nothing. So that carbon would have the lowest priority of these 3 carbons. Well, what about this? This guy's got 2 hydrogens. The more hydrogens you have, the more you associate with these lowly hydrogens, the lower on this priority list you will be. So your associates are very important here. You got 2 hydrogens, you got 1 hydrogen. Besides, so if you take this carbon here, this carbon is connected to 2 hydrogens and a carbon, right? If you take this carbon here, it's connected to a carbon by a double bond. So it has got 2 carbon-carbon bonds and a hydrogen. So this guy pretty much has connections in high places. This guy's got associating too much with hydrogens. So, well, this is lower priority than this. So the higher atomic weight groups that you attach to, the higher your priority. So therefore, this is going to be 1, then this will be 2. This is going to be 3, and this guy's got too many hydrogen friends, not good. So that's 4. Right, so then we got to put 4, it just so happens that I drew 4 away from us. And so therefore, you can just look at it. You don't have to switch this molecule around. 1, 2, 3 here. And I'm making a left turn, C, S. Here's 1, and 2, and 3, and 4. 4 is away from me, just like before. So 1, 2, 3, I'm making a right turn. That's an R. Always an R will be reflected as an S because it's a mirror image, and so therefore the orientation is different, is flipped. So that's one way to do R and S. We'll do a few more problems over there. And let's say you have a huge molecule with lots of chiral centers. How are you going to do that? So let's look at this molecule and see how many chiral centers are there. It's kind of complicated, making your head spin. Well, this molecule is enough to turn anybody's head around. So let's look at this molecule and do it just like you would do any other problem, just one at a time. So over here we have a carbon here that's got, well, 2 carbons attached to it, a hydrogen and a hydroxyl. So since we have 2 carbons, does that mean it's achiral? Well, you got to go all the way around to see if it is symmetric or if it has a symmetry or not. So if you take this and if you cut this in 2 with this cake knife, you can see this part is different from this. So obviously there is no plane of symmetry. All of these, whenever you see a CH2 here, well, you know when you have 2 things that are identical, like 2 hydrogens here and 2 different groups here, you can cut it right in the center here and get 2 equal halves. So you can do this by just purely by a method of elimination. So CH2s are achiral. Same with CH3s. We got 3 things, so obviously many plane of. If you have an alkene, we just said if you have sp2 is a flat carbon, and so you can cut this right in the center like this. So any sp2, carbon-carbon double bond, or carbon-carbon triple bond. I know we don't have triple bond here, but you know you can cut this in many. 360 all the way around, you can cut it in 2. So that's achiral. So all of those we can eliminate. And if you have like a isopropyl, well, that's going to be achiral. A T-butyl would be achiral. So all of these, if you see them, you know they're going to be achiral. So therefore, all this, I'm going to cross out all of the ones that we just talked about, all of the CH2s and the alkenes. And here's a, well, is this chiral? Let's say methyl, 2 identical groups. It's almost like an isopropyl there. Although it's drawn kind of to tricky wedges and dashes. So just because there's a wedge and dash doesn't mean it's chiral. You got to make sure that doesn't have identical groups on it. All right, so then the rest, let's say, we can see if it is chiral. Yeah, you cannot cut this in 2. This is chiral, so we can star it and say this is a chiral center. Over here, you got a carbon. It's connected to 3 different carbons, but all of them are different. So if I cut it in 2, this is different from this. If I cut it in 2, up is different from down. So there's no plane of symmetry here. Same here. All the 3 planes there are different. Left is not the same as that. Bottom is not the same as the top. They're different. So that's a chiral center here. Same here. These are all different. So therefore, you can see that that doesn't have a plane of symmetry. Same with this carbon. Left and right are different. Down and up are different. All the planes of symmetry, all of the planes are symmetric. So here you don't have a plane of symmetry. So same here, you don't have a plane of symmetry for this. There's a hydrogen here. And what about here? There's a hydrogen and methyl and this long chain and there's 4 different things. Chiral. So if you're given a big molecule and asked to identify the chirality, you just have to go one at a time and first eliminate all of them and then go in and see if they have a plane of symmetry or not. So then how do you assign R and S? Let's just do it for this one here. Here's a hydroxyl. Oxygen's heavier than a carbon, so it'll be higher priority than this. hydrogen is the lowest. Between 2 and 3, well, this is CH2 and this is CH2. So there's no way you can decide just by going one carbon over. So you go to the next carbon. Well, this has got more hydrogens, lower atomic weight friends. Not good. This guy has got 2 carbon-carbon bonds, 3 carbon-carbon bonds. So therefore, this has higher priority than this. So this is going to be the chain that has like high atomic weight groups attached. So this is going to be your next highest weight, heavy weight. Then 3. Okay. So here 4 is already away from me because it's on a dash. I don't have to rotate it. And if I go 1, 2, 3, it's going left turn. That's C. So that's one way to do RNS. Let's just do our thalidomide before we are done for the day. Here it is. So here's your nitrogen, carbon, carbon. So and hydrogen. Obviously, hydrogen would be number 4, lowest priority. Nitrogen is heavier than carbon. So in between these 2 carbons, this has got 2 carbon-oxygen bonds and a carbon-nitrogen. This has got 2 carbon-hydrogen bonds and a carbon-carbon. Obviously, carbon-oxygen, high priority. So that's number 2 and that's number 3. Now, hydrogen should be on a dash facing away from me. So therefore, I should really draw this molecule like flipped. So that's too much work. What I'm going to do is I'm going to assign it just the way it is. And in my head, I know that if the hydrogen is out, it should be the opposite of this. Because look from the opposite of the lowest priority group. So that means if hydrogen is away from me and it is R, then if its hydrogen is towards me, that same orientation would be S. So that's something to remember, because otherwise it takes a long time to redraw it. So 1, 2, 3 is going clockwise. Clockwise is typically R when hydrogen is on a dash. Therefore, when hydrogen is on a wedge, clockwise would be S. So yes, and that's correct because S-thalidomide was the tetragen. So I will see you soon and we'll do some more problems, guys, before we go on to other topics like diastereomers. A quick summary here. We talked about stereoisomers, molecules that have the same molecular formula and connectivity but different spatial orientations. So if you take 2 molecules and they have 4 different groups on them, they don't have a plane of symmetry. That means you cannot cut it into equal halves. So therefore, those molecules are called chiral molecules. And a chiral molecule can have a mirror image that is not superimposable. That pair, let's say this is a molecule and this is the mirror image. This pair, these are called enantiomers. And we want to tell enantiomers apart when we order them. So we use the handedness or the clockwise and counterclockwise orientation of these groups in order to label them as different molecules. So we use the CIP rules for that, which is find the stereocenter, assign the groups according to the atomic weight of the element or the atom that's attached, and then if the high priority to low priority goes counterclockwise, that's S. If high priority to low priority goes clockwise, that's R. See you soon.